Well, good morning. Thanks for tuning in with me today. I thought today I'd do something a little bit different. Instead of working on something live, I want to walk through the current implementation of adding debug info to the binaries that the language outputs so that we can debug our programs in GDB or LLDB or really anything. LLVM supports this really nicely, so all I've really done is use the API, but I thought it might be nice to do a little demo. This has helped me immensely with debugging code gen issues and things. So I think this is just really cool. I have a program here, a.nx, and what we have here, let's go 16 point. What we have here is an array of points, 3D points, and named x's. And we loop 100 times, pushing a new point into the array. The array will grow a few times, so we're going to log the capacity and the length at the end of this, and we'll see that the grow method, inside the array has triggered a few times, and that's sort of a classic double the size memcopy thing. So it's a nice program. It's a great milestone for me because we can see that in memory we have a contiguous array of all of these structs. We don't have an array of pointers. We'll look at that. We'll be able to see that in the debugger, and then I'll walk you through the code and how that's generated and look at the LLVM IR with the debug info. So for starters, here we are in LLDB, and I'm slowly learning a bit more LLDB, but mostly what I do is I break at main and then I run. So we'll go ahead and do that, and let's break at main, and let's break at main. Okay, so no, at a.nx line, we'll say, let's get an absolute line number here, line 23. Okay, and we can see it seems successful. It sees the actual offset in there. So let's just run, and this is already amazing. We have, we're broken here at our function. This is our source code, and we can see it here in LLDB. So what I can do is I can run frame variable to see all the local variables in the current stack frame. Now we should expect to have two. We have x's and I. We see that x's, LLDB knows a lot about our types. It's an array of records, and it's a pointer because our arrays are always modeled as references. We implemented reference types in a previous video. This is because when you have an array, you almost always want to be able to call push and grow it and mutate it. So it just makes sense to pass around the reference to the thing rather than the actual struct, the three-member struct, which is the length, the capacity, and the data pointer. Yeah, so we tell DWARF that it's a pointer type, and it's able to just look and find everything. So, and then we have the long I. So our ints are longs, really. They're 64 bits, which is something we may change soon. So I can go ahead and do an S, which is going to step one instruction in the source. You see now we're on the first line, and if we frame variable again, I is still 0. X is no longer null. We may be off by 1 on our line numbers, because as you can see, x's has now been set. It was null before, so that's interesting. We could just frame variable after each run. Let's just step, step, step. We'll step through one iteration of the loop. So we'll step again. Okay. I don't want to step through all of the zig code and this int to char thing just for print line. So let's break at line 13, or maybe let's break well, let's just continue, okay? So we'll continue, which puts us at the end of the loop. So we run the loop 100 times. We'll frame variable. We'll see that I is now 100. We have an array still. And this is what gets really exciting. So we can print, and it's sort of C style syntax. So for a dereference, we have x's length, and the length is 101 because we had one element and then we pushed 100 times. Capacity should be a power of 2 since we double it, and indeed it is. It's 128. That's just really cool. That I think this is amazing that LLDB knows about our completely custom types that we've built here. X's also has a data pointer, so let's just print X's actually. So you see it's saying it's a pointer here. Okay, so let's dereference it and then print that. Okay, well, it's this type, array of XYZ, and we could probably use the name point here. That's something to think about rather than fully exploiting the full type definition, but I think it's kind of cool. Anyway, we can see all 3 fields here. So the data putter is this. Let's dereference that and see what's there. So it should be a pointer to an array of not 101, but 128 structs. And each of these structs should take up 64 times 3 bits. So let's p-array. And how many do we want? Well, we want x's capacity. And what array? X's data putter. And we can see all our data here laid out contiguously in memory. Let's set x is at 50 to something else. Just for fun. So we got to recompile. Debug no LLVM opt, so we'll run here. LDB again. Let's be main, be a.nx line 24 and run. Okay. Frame variable. So well, that's interesting. Wonder if array assignment is broken right now. We definitely, and we're breaking at line 24, and we'll run. Maybe array assignment's broken. So let's fix that, and then we'll continue on our debugging demo train. Recently did a good bit of refactoring here, so I'm expecting this to be a pretty simple change. So array index seems to be doing the correct thing. We code generate index operation, which always gives us a pointer to that location in the array. And if we're in assignment mode, then we just return that pointer. Otherwise, we're going to load it and return the value. So let's go to the place where, so now we have an array index, but within the context of an assignment. So we're assigning, and the left-hand side is an array index expression. And we do the right thing. So we should get a pointer value, which we do, or we would have crashed here in CodeGen. And now we evaluate the right-hand side as an R value normally. And then we store the right-hand side into the pointer. So this should be working. And I have a program called ArrayFill, which assigns to an array like this. And I believe it's working. Resources, test source, array fill. 4, 4, 4, 4, 4. So I wonder what's up. Let's sanity check things. Let's print. These 3 things. That took a long time to run. Did y'all see that? That was interesting. 100, 200, 300. So it is working. a.inx.out ldb b maybe it's our line number bug. Let's break at line 28 and then run. That looks like line 28. That actually seems correct. I don't think we're off by 1. How could it be? How could it be? If we are able to print the correct thing. Int char. This is all for print. If I continue, then we're just done. So, is there a chance that in our debug info, X's is still pointing to the wrong address? Well, every time it grows, it seems to get reassigned because it's pointing to the correct thing. Oh, well, actually, only the first 101 should be 1, 2, 3. So maybe something is going wrong in the maybe when we grow and mem copy things, we're copying too many or something. It's really interesting that this is correct. So I would think that the debug info, we can, yes, dereference this. Is this, so it's looking at X's on the stack frame, which we set, when X's grows, so in array grow, I've put a print in here straight in the code journal, which is a really useful thing to be able to do now as well, because these all correspond to a single instruction in the source, but maybe we can print, you know, to know where things go wrong if we litter this with a few prints. But so this is grow, and essentially what we do is we mem copy the data, we allocate a new array, we multiply the old capacity by 2, and we store the new array into the existing stack pointer. Well, not stack pointer, just pointer, right? So nothing should be needed updating debug info wise, because the actual location of X's never changes. So we simply take the old array and we update its data and capacity. We don't update its length, because when we grow, the length doesn't change. We could take a look at array grow, just called grow, should probably be prefixed by the namespace in here. This is we can see the debug info here actually. So whenever we have a variable, the secret sauce is to call this LLVM intrinsic and declare it. We pass the reference to the instruction that corresponds to that variable, and then we pass it references to some metadata nodes that contain type info, debug info. This is the source location usually. So, you know, at the end of each line we see we're adding a source location. We're storing into loaded value in the very end our new array with its capacity and its new data. And loaded value is whatever is in self 1. And self 1 contains, you know, what we got from self. So I think this is all working. Be interesting to debug before and after grow and see if the data pointer changes. Anyway, enough on that tangent. Let's dive into the debug info here. So what's necessary is to So in addition to a DI builder, not a DI builder, the LLVM IR builder that we use to create instructions, you know, say builder.build store, build load, build add, build if, right, to emit instructions. There's a debug builder as well. So we simply have to create a debug builder at the beginning for our compile unit and use it to create these source locations and to attach debug info to our instructions. So when we allocate a variable, we then also say, hey, do a variable declare. We ask the debug info to emit a variable declare, and we point it at our stack variable. We'll look at that in a second. So what I have here is I have a stack of scopes so that we can always know the current scope, and when we exit a function or exit a scope, we can pop back out. This is just a little cache of our AST scope ID, or really our IR scope ID, to a debug scope, so we don't have to generate them over and over again. We do a quick lookup. And then the builder I mentioned, and then the file, because it never changes. And we need that for almost every source location build. So we can look at where this thing gets created. I pulled it out in a separate function because it's actually 60 lines or so. To do need source path. I actually fixed this. See, we have as part of this, I added some stuff to source, everything that's needed for debug info, so that we can like see the source code. So we have the actual directory file name that we didn't have before. So we're essentially just calling LLVM module create debug info builder, which Inkwell gives us. It's essentially just calling, you know, straight into a function in the LLVMC API that takes all the same stuff. So we say that it's C because it's the closest thing, especially based on how our data is represented in memory. Bunch of info. I added this because Clang was doing it. I kind of just tweaked these settings. I would just compile a program with Clang with debug and look at the LLVM IR. And if anything was different in mine, I would change it so that it would match, because the debugger was working when I would compile a C program with Clang, but it wasn't working from mine. So a lot of this is just reverse engineered from running Clang on a simple Hello World C program. This, additionally, I couldn't find any documentation really online on whether these were necessary or not. I know the DWARF version is needed, and again, I just omitted metadata nodes until it looked like what Clang was outputting. So if we scroll down to these metadata nodes, we'll see, yeah, LLVM module flags, 2, 3, 4, 5. That's this, right? So all of this code amounts to setting these flags that are used by the debug info. We have our file here, as you can see, our directory and the file name. And then we start a subprogram. Oh, no, subprogram is just a function. So we have a compile unit, sort of the main entity. You see that's bang 0. See, the subprogram points to the compile unit. Everything underneath that points to a subprogram within a function. We can look at, so what does printint return, right? The type, well, not what does it take and what does it return? That's here in the type. So type is bang 8. Go to bang 8, it's a subroutine type, and the types are 9, so we go to 9, and we have 10 and 11. So the return type is first, so it returns unit, which I'm telling DWARF is a Boolean, because I represent my unit type, I think, as a Boolean true, maybe as a Boolean false, I'm not really sure. And then it takes an int, and that's assigned integer value of size 64. So this is how this is sort of DWARF speak for different types. Let's see, what is 12 used for? Retained nodes, local variables. So the print int has these retained nodes. So we point down here and say, okay, 13 is a local variable named value. And the location is kind of fun. DI location, line 0, column 1. So let's go look at printint in the prelude. So we're talking about the debug info for this function here, the first non-external function. And you see that the parameter is named value. And that's what this is referring to. So that's why when we're inside that function and we say like frame variable in LLDB, it knows that there's a variable called value. And hopefully is pointed to the correct location and memory too. And that's all taken care of by LLVM. I just sort of have to line it up with the instruction. And then, you know, it's just more stuff. We have composite type, we have structure type for string. Our string is a length and a data pointer, so it's really a struct. So if I were to debug a program, I think I have hello string. Or maybe it's string hello. Hello. Let's take a look. String, string, string. Well, let's string concat and let's break on line 3 and look at it. I think debugging the strings works. Resources, test source, string concat. Now we'll LDB string concat b string three. My shift key might not be working. You guys have seen a number of mistaken hyphens instead of underscores. Okay, we run. Now let's frame variable. Okay, so X is a record, but we name it string, but it's a composite type. Length and the data is ABC. It's so nice. I think we haven't concated yet. So if I step one more, maybe we're in the middle of this. So now the data's been reset or something. Yeah, I think we've gotten off by one issue with our breakpoints, with our line numbers. Well, we don't need to see it after the concat, but the point is that we saw the length and the value, which is pretty sick. Okay, so I make my debug context, which is just where I store all the debug stuff to not clutter up the main cogen struct. Yeah, the aforementioned stack, the scopes. I push the file scope as the beginning, and then we're off to the races. So all I have to do is call init debug and the main create to have that available. And now let's just look at maybe typed expr variable. So in a variable declaration, okay, so for any expression, we set debug location expr gets span. So we have a helper to set debug location, calls into our debug builder, creates a location, and then we are using our source span info here. So this just happens for free for every expression. Really nice. I'm trying to find where I actually declare. Oh, this is referencing a variable. So what we actually want is the block statement. Really, the statement level is where we're going to do a lot of this debug info stuff, because a statement is like a line of code, right? You can have a lot of expressions within a line, but you're going to have that one statement usually. So for a val def, so we call into cogen val because there's more going on. And look, we're going to do debug stuff now. So this is the store instruction, which we keep around now. Previously, we don't need the instruction. Build store returns the instruction. But now we do, because we're creating, so insert declare before instruction. So the instruction is the store, and it's a declare. And what are we declaring? Well, we provide the variable, and then we point LLVM to a DI local variable. We don't give an expression. We do give it a location, and we give it our instruction that we're inserting before. So, you know, what is this? Well, it's an auto variable because it's a stack variable, right? So create auto variable, and then it just takes a bunch of stuff that's you know, kind of available. You know, our debug info makes this, our debug context makes this kind of useful because we can just say current scope. The stack will never be empty. If it is, that's fine. We can crash during compile and fix it. We get the name, the file, all this here. You know, this could be moved into a helper, but it kind of already is, right? I mean, there's only one place that we could gen a variable. So yeah, and that's kind of it. And then apart from that, so that's location and that's variables. And then we do the same when we enter a function. We declare a variable for each parameter. And now all we really have left is the types, right? So it's exactly what you'd expect. We're going to get type. There's some constant flags here. These are dwarf constants that correspond to, you know, this is what allows us to actually see ABC when we were looking at that string earlier, because we're telling dwarf, hey, it's a bunch of characters, right? So these are how we tell it about known types. Same with Boolean, we'll see true or false instead of 1 or 0. How to interpret the data, really. So we get type and we just match. So for unit, it's just this create basic type for our scalar types, which doesn't take too much. It's like, what's the name? You know, how big is it? And then this encoding flag. So like, how should I display this? We do unit as Boolean, Boolean as Boolean, character. We're in luck. We have character, int. It's assigned int. So there we go. String. Okay, this is where it gets kind of fun. We say create struct type. We give it the name. We just hard code the size. For a built-in type like this, I think that's fine. Although this should actually be, well, it's kind of word size bits times 2, but it's kind of, it should actually be, oh my bad. If we wanted to make this robust, the correct thing to do here would be to say, okay, the width of our int type for the length plus the width of plus the platform word size bits, which I have hard coded to 64, but at least we indicate here that it depends on, because we have a length and then a pointer. Let's say length was 32 bits, then that would be 32 plus 64. And then the alignment, I'm not sure, you know, I'm just making a match. So I guess this could be 64. Anyway, we're creating a struct type, and so it takes all these things, and then it takes, hey, what are the values in the struct, right? And within each of these, this was a trick. I was just putting types, but you can't do that. You have to create member types and put them in there. So we're putting a member type for each of these structs. So the string is just string length and string data. Again, all our debug info stuff, the sizing, alignment, that stuff. And then, okay, the member type actually takes another type. So what's in there? So I just recurse into this function for int to get the type in there. And then for the data, we can't recurse into this function. We actually just create pointer type right there. We say, hey, it's a pointer to char. So we do recurse in. And that's what allows us to just see it right there in LDB. You know, this creates the right layout so that it can navigate, dereference the pointer, and show us the data there. Really nice. For record, it's kind of the same as string, but it's dynamic. So we're just going to say, hey, for each field, generate a member type, and you know we've got a little offset up here because you know the offset, the size is different for each member, so we just increment the offset each time, return that, collect that into a vec, and that's our debug type for any given struct. That's what let us see the 3D point XYZ earlier. Type variable, this is generics. We don't code gen anything for type variables. There shouldn't be any. And array, same thing. It's like string plus a capacity. So it'll look very familiar. Optionals. Optionals need some love. I implemented them before this sort of overhaul to like how we handle references and returning structs as aggregate values. All the tests are passing, they're working, but I think I need to do a little bit of work here to get the debug info looking nice. I say create struct type, I give it no elements. This is sort of just a punt. You know, I could fix me here to do, we are punting on the debug type definition for optionals right now. You might say, why add this here? Because, well, you can see it, it's very obvious. It's so that I can sort of search for to-dos throughout the project and kind of browse if I ever just want to address a couple to-dos. You know, it's sort of keeping inventory or to see it next time I'm here. Okay, and then reference, which we did. So this should probably, I think we can just do star. This was a little copilot love. Yeah, so reference, and then we just say, hey, well, you know, it's a pointer to whatever the inner type is. So this actually works. This should not be underscored. Oh, right, reference type is fine. Okay, so we did a little bit of cleanup. And that's about it. So, you know, that's how we attach type info to things. Let's look at, let's do, I wonder if there's a better program to look at. Also, I get syntax highlighting, so let's do this. Let's NeoVim, well, let's NeoVide, so it's pretty. NX out, let's do this namespace. Okay, it's a little small, but at least we have a little bit of highlighting. So I just want to highlight the debug info. Just results in a bunch of these intrinsic calls to value and declare. Value needs to happen on assignment. Maybe that's what I'm missing. Maybe I need to call dbg.value to update the value when something is assigned. Yeah, that makes sense, actually, because I'm doing the declares correctly, but maybe not the values. Anyway, that's about it. So what happens is the compiler then sees this IR with all this debug info in it, and it generates the platform appropriate, you know, we even say in here to output DWARF, so it generates DWARF data. Actually, let's do that. So we can DWARF dump. Let's do our a.nx that we were do we need to .dsym? Yeah, we do. Okay, so here's the actual DWARF. A lot going on here. We could try it with no prelude. So let's do a no prelude file. Yeah. Let's do int add without the assert. Cargo run int add. And then we're going to need no prelude. Okay. Let's do this again, this time hopefully with sound. So we compile int add with no prelude just to make things kind of small, and now we'll DWARF dump and we can see stuff that looks familiar from our program and looks familiar from the flags and the DWARF info that we were adding to the LLVM. We see a subroutine call add stuff, we see the file, you know, we see our variable names, result, x, main. We don't have any interesting type stuff here because this program only had ints. It looks like it strips stuff we don't use. Be nice to just like add a string just so that we could see how they're represented. But you know, you can kind of just imagine it's the same. It just says, hey, composite type, and then, hey, member type, and you know, and then they're just there like this. So this is the raw data extracted from the object file. I guess the debug directory. So I'm not, you know, it's stored separately here in Mac OS on Darwin, I suppose. I'm no expert, but yeah, I just, this was a big milestone for me. One, I thought it'd be useful to make a little video because getting the debug info working was a lot of effort, and there were some gotchas, and you know, nothing really tells you when it doesn't work. I guess the last thing I should show is the actual build command. So you gotta compile with -G. Make sure you're pointing at something that actually does have debug info in it. So I'm now compiling I'm pointing Clang at the LLVM instead of at the object file, just because it seems to make a bit more sense to do that since I'm really omitting LLVM. I know this isn't as fast. I should do the in-memory one and then like pipe it and that sort of thing, but you know, this is where we are right now. Yeah, it just felt like a bit of a mark of legitimacy that all this established debug tooling that's built for C and, you know, Swift, other native languages, that it's able to inspect the data of the running programs in my toy sort of custom language and actually make sense of them. It's just really neat to see the data actually laid out in memory in a way that kind of makes sense to, you know, a real debugger. And it's really useful. It's going to save me many hours down the line of troubleshooting. So yeah, hopefully you found this interesting, or if you are ever looking to do the same, adding debug info via LLVM, maybe you'll find this video a nice resource. As far as resources go, the adding debug info to Kaleidoscope, the chapter 9, was really helpful. I think it could include a good bit more info about specifically things you might need to do to set up to make sure it actually works. But the thing that I found most helpful was just compile a simple C program and emit the LLVM with debug info. Let's go ahead and do this. Let's look at what it outputs. This is the best form of documentation, right? So try and make it do basically what Clang is doing as far as debug info is concerned. You can see the declares here. It looks pretty similar to what we had, and you'll have success that way. So yeah, thanks for watching. See you next time.